Okay, so we're going to look at Chevyshev's inequality again, and we've seen this before, but I'm going to show you another proof. I'm going to show you a proof in the continuous case, just so we can sort of play with more proofs. So here's our Chevyshev's, and remember the whole idea is it's going to give us bounds on probabilities. We don't know what distribution we not have, we just know in this case it's going to be a continuous random variable. We have an expected value and a finite variance. So let's go and look at the proof. So if we come to here we are, here's the proof. So let's break it down and see what's happening here. So first of all, we start with our usual thing of, we're going to start with, in this case, we'll start with our variance. And we write what this is. Remember, the variance is the expected value of y minus mu all squared, where we're using mu to denote the expected value, just to make it easier to have lots of expecteds in there. And we know that this is a function of a random variable, so we write the function then f of y. And all I've done in this stage here as I go from here to here is I've taken this region of minus infinity to infinity and I've split it into 3 bits. So the first bit goes from minus infinity to mu minus k sigma. Then we go mu minus k sigma to mu plus k sigma, and then finally we get the last bit. And all we've done is we've split it. Look at each of them regions. What we've got is we've got something here. So we've got this bit here, which is y minus mu squared, which is always going to be non-negative. We've now got this bit here, the f of y, which is non-negative. When we multiply that, we get something that's non-negative. So each of them integrals, we don't know the answer, but we know that it's going to be 0 or positive. So the fact is, we realise that when we look at this segment here, I don't know the value, but it's going to be greater than or equal to 0. So if I now write it without it, we can now get a greater than. Remember that trick we talked about last time that keeps coming up? Some of you students have suggested it should actually be made an official Gary Glonick trick. There's a big process to go through that and sort it out, but you know, maybe we could. But we've got to that stage there. And let's pretend that's Coke. So, what about this next one? This next one, when we go from here to here, is a big jump. And I want to break that down. I think that's worthwhile spending some time trying to work out what's happening there. So let's choose a region. And I think the region we'll take is, we'll start by looking at this region here. So we're integrating from mu plus k sigma all the way to infinity over y. So y goes from mu plus k sigma to infinity in this region. So let's think about that region. So in that region, we know that y will be greater than or equal to mu plus k sigma, because that's the region we're integrating over. So I can rearrange that and say this is y minus mu is greater than or equal to k sigma. If we square it, get y minus mu squared is greater than or equal to k squared sigma squared. And I'm going to write this as y minus mu squared f of y is greater than k squared sigma squared f of y. Why? Because I've just multiplied both sides by a PDF, and a PDF is 0 or greater. So you're not going to change the inequality. And that's the key thing with inequalities. You've got to be very careful about what you do, because you can actually, if you times by a negative number, you'd have to flip. You'd have to reverse that inequality. And that now means that the integral of y minus mu squared f of y is greater than or equal to k squared sigma squared f of y. What's happening there? Well, there's a rule that you probably were told in first year, and like all the rules in first year, you probably forgot because they never actually told you it would be useful. And what is that? It's basically if I have f of x, and that is greater than or equal to all of g of x over a region from a to b, then basically if I integrate from a to b f of x dx, it will also be greater than or equal to the integral of a to b g of x d of x. And if you think about it, what we're saying is, if you've got your picture here, here's your A, here's your B. I don't know what G does, it's like this, but everywhere we go, F is greater than it. Here's my F, here's my G. So now when you work out your areas, you know this area is going to be less than or equal to this area. That's all it's saying. So, oh, forgot the integral. So we've got this is true for that region. If you go and do the other region for y less than, or what is it? Let's go back. If you look at it, it's the region that y is less than mu minus k sigma. Basically, you'll find that both of these regions are greater than or equal to the associated region. Okay? So now let's just clean up so we can actually see this. So we've got a k squared, sigma squared, k squared, sigma squared. These are constant, they can come out the front. This one's constant, it can come out the front, which is what we've got here. What we've got now, I've got a PDF and I'm integrating from minus infinity to mu minus k sigma. And also this one, I've got on PDF and I'm integrating from mu plus k sigma to infinity. Well, this one is the probability that our random variable is less than mu minus k sigma, by the idea that we get probabilities by integrating. This one is the probability that y is greater than mu plus k sigma. Got our thing out the front. And this is just equivalent to this, and we can rearrange it because that equals our variance right at the start. So we've got our sigma squared. So we now know that sigma squared equals this. You rearrange and you get this. Okay, so there's another proof of Chebyshev's inequality. And next time we'll start looking at some named continuous random variables. Okay, see you next time.